Oh, we'll do it right now. Let's see. Let's see what else we can do with this. I'll set it up and we'll finish it after. Why doesn't M2G become negative when you move to the right side? Okay, in the next problem, I'm going to take you through the exact way to do the negative signs. That's why I blew it off there, so we don't have all day. So we're going to do the exact negative signs, even more correct than the book. Okay, I'll even show you where the book sells you out here, and you're going to see it all. So let's just get it set up, and then we'll do it in the second half. So we just agreed that normal forces are not always equal to the weight, and we're also going to check that normal forces are not always vertical. They can be any direction. And I'm making these contrasts because if you've only ever done simple problems, then the normal force was just a quick trivial thing and you pointed it up and said it's equal to the weight, but that's not the case. So what we're going to do is take, I guess we'll put this here and say, what if the ball is like this? I didn't test this ahead of time. I don't know what's going to happen. Like that, okay. So the ball's like that, didn't go anywhere. And the ramp is at an angle. Everybody can see. Okay. Just look at the drawing. Okay, there we go. Let's just look at the drawing. So let's say we have a ramp like this at some angle theta here, and we have a block here. So this is all stationary stuff, not going anywhere. And we put Hal here, a ball of mass m here. And we're going to call this surface A, and we're going to call this surface B. All right? So we want to find the normal forces. Right? Which way do they go? How big are they, etc. So let's do the free body diagram first, and then we'll obsess with the math later. Okay, so free body diagram. For the sphere, here it is. It's a point. We'll draw mg down. That's the weight of the sphere, mg. There, see, I switched to mg instead of w. Yeah, no, I already answered that. Okay. And now we have two normal forces, and which way is the normal force? It's always perpendicular to the surface. Right? So now I've tilted the surface, so now they're off at an angle. So we're going to call this one the normal force of B, like that, because that's surface B pushing on the mass. We're going to make it a little simpler. We're not going to use two things because everything's pushing on one thing. So we're not going to write BM and AM. We're just going to call it the normal force of B. So you've got to make these decisions when you get started. Right? And there's also a normal force of A, and where is it? It's perpendicular to the surface, like that. Normal force of A. So the question we're going to answer is we're going to find in A and in B in terms of M and theta and G. Okay? Okay, so we'll do that in 5 minutes, if you can wait. Okay, let's do this problem. Here we go. It's going to be exciting now. Oh, wait, one question. Oh, there's always one. What if the thing is so heavy it destroys the table, right? So then it's not a normal force anymore. But we are living in the ideal world of, pretend world of intro physics, where, you know, certain things are just stuck and don't fall, and you can't deform anything, et cetera, et cetera. But yeah, if you crush it, then you're doing like contact mechanics, and you're doing real world stuff, and we don't talk about that here, so let's not get into that, okay? Okay, so now, very good question. As you know, and I actually did it on purpose, is when I did the two normal forces at the same time, I said, oh yeah, some algebra, this goes over there, don't worry about the negative sign, and here's the answer. That's how we do most physics problems. Oh, here's some components, and oh, that negative, well, because it's the other way. The negative's wrong at the end, probably something was the other way at one point. Here's the answer. That's how we do intro physics, if you ever notice. Okay, that's how you do it, that's how I do it, etc. So now, this problem, I'm going to drag you through exactly what you're doing between vectors and vector components and polar and Cartesian all the way through. We're going to do it once. Okay, I want you to see where all the weird negative stuff is happening, and then I'll go back to the normal way. Okay, so if you're ever confused about where'd that negative come from, you need to go look at these notes again. Here we go. All we're going to do is say this thing was sitting here. The point was the normal forces can be weird directions, and let's get these normal forces. Let's get the magnitude of these normal forces. That's what we want to do. All right, we're going to do it in a normal Cartesian coordinate system, x this way and y that way. Okay? And we don't even have any, we only have Newton's first law, but that's all we need because it's not moving, right? It's sitting still. So we said Newton's first law says there's 0 net force in the x direction. That's one thing we know, right? So we need to add all the forces in the x direction and set them equal to 0. And how are we going to do that? Vectors, components, polar, Cartesian, magnitudes, directions, or just put some letters and not worry about it, right? So let's think. Let's write it like this. Let's write it as x components. After all, we are in a Cartesian coordinate system. So it would seem we might as well use Cartesian coordinates and write components, okay? Components of the vector in A and the vector in B. Okay? So if you're writing components, the standard thing to write is to say in A, x component. And now we want to add the in B. So you can see in A is kind of positive, and in B, the component, we could draw them like that, is kind of negative. But you don't put a negative sign on a component. In B, x equals 0. Okay? Don't make components negative. Because you're letting the equation tell you whether or not it's negative. If you program in the fact that it's negative, then the equation will just tell you the magnitude, probably. But if you really want to know, like, if you can't look at this and you can't tell which way in B is, then that's okay. You just write this. We'll get the negative part later. Okay? So if you're seeing something written with little components, little x's, you don't make it negative. Your book kind of goes through this on page, the third edition is page 140, section 6.1. My fourth edition was at another place I couldn't check. But in their little box, when they're talking about adding up tensions, I think, they sort of walk through this. You don't make components negative. Now, calculate the components. Components. And are they given to us in polar or Cartesian? They're given to us in polar. We have a drawing. We have the length of the vectors kind of represented. We'd like to figure out what they are. And we have angles. We have thetas, because I told you the theta right there. So we are in polar. So calculate the components from the magnitude and the direction. Okay? All right, so here we go. That's what we're going to attempt to do right here. Okay. So we say, how do we get the horizontal component of this vector? Right? Basically, we are converting from polar to Cartesian. Right? The horizontal component, the x component, is Cartesian. This is polar. You may remember it was the length times the cosine of theta. Right? So that's all we got to write. Why do the normals equal 0? Because it's not moving. It's not moving in the x direction, and Newton's first law says an object at rest remains at rest unless there's a force on it. So if it's at rest, there must be no force on it. So that's why the forces have to add to 0. Okay, so let's write it down. Here we go. X component of NA. You ready? Here it is. It's NA, the magnitude, times the cosine of theta. Right? This is the magnitude. If I write a vector without the arrow on top, that's the magnitude. Okay? It's not the vector component in x or something like that. If I put an x on it, it's a component. It can be negative. If I leave nothing on it, it's a magnitude and it can only be positive. That's the technical rule that we largely follow. Sometimes people might forget to put their x on here and write it this way and mean the component, but they wrote it as a magnitude. To play it safe, you can constantly write NA with a vector sign and 2 bars. Everybody hates that, right? It's ugly, it's messy, etc. So I just want to be clear that I just meant magnitude right there, and I meant the polar angle, and this is the standard angle. The magnitude there, standard angle there. Standard meaning, defined counterclockwise from the horizontal axis, which is basically how we define this one. That was easy. Okay, now, what about the second one? Now that we're getting, not components, now that we're Whenever we're calculating the value of the components, it's this way, isn't it? Is this when you put the negative in? This is when the book says to put the negative in. And if you're like some basic pumpkin spice latte sieving pre-med, you would put the negative in. But we're not going to do that. We're going to do it right. You put plus. When we talked about polar to Cartesian, did we put negative signs in things? No. We said all it is the magnitude times the cosine of the properly defined angle. Okay? So we're going to say plus the magnitude in B times the cosine of the properly defined angle. And what is that? Theta plus 90, right? This is 90 because this is 90. I didn't tell you that, all right? So those are perpendicular to each other. So the angle is the counterclockwise from the horizontal axis. So theta plus 90, all right? That's the way you do it. I didn't fake any negative signs. So I faked anything, no. I didn't put any I didn't artificially put in a single negative sign. And now I'm going to say NA cosine theta, and I'm going to Google. I literally, last night, Googled cosine of x plus pi over 2. That's how I find these things out, okay? I don't have them memorized. If you Google cosine of something, it just shows you a little graph. And I looked at it and said, oh, that's a negative sign. That's how I figured out. You find your own way. Minus NB sine of theta, okay? Has to equal 0. So there is where the negative sign showed up naturally mathematically. It just showed us by using a trig identity that if we define this angle here, that means it's really this angle here. The reason it became a sine is because this angle is this angle from the vertical, so the sine is the x component. And the negative sign showed up because it's in the negative direction. But really, we just applied a trig identity right here. All right, that got some questions going. Here we go. Isn't the angle 180 minus theta? No. Look at the angle more carefully. So when you want to think about which way is an angle, take this coordinate system and just turn it. Right? You're thinking that this is theta, but this is theta. Unfortunately, I drew it at about 45 degrees, so it's hard to tell. Okay? But imagine this ramp were just barely rotated. Then this NA-NB thing would just be barely rotated. And here's theta right here. Okay, so it rotated theta, and then we have the plus 90 because it was originally 90 and then theta. But yeah, you got to watch those very careful. It's easy to miss. I understand why you had 90 degrees to the angle. So I just said again, well, because the definition of getting the x component of a vector when you go from polar to Cartesian is you take the magnitude times the cosine of the angle counterclockwise from the x-axis. That is the definition. That is just math. So I said 90, and then theta, 90 plus theta. Does anybody know the hustle? No, okay, I don't either. What was weight force? Why was not weight force not included in the sum? Oh yeah, let's add the weight. There we go, because it's vertical, right? It has no component in the x. Right? That's why. Oh, let's put it in. What the hell? Let's see. Plus mg cosine of negative 90. There you go. What's the cosine of negative 90? 0, right? So that's the magnitude times the cosine of negative 90. You've made the lecture better, if that's possible. So this equals 0, right? So plus 0 equals 0, right? So that's the proper mathematical way to do it, right? That's all it is. Now, the book tells you, oh no, put a negative sign in and call it sine, and just define the angle here. Oh, right, no, don't do that. Or you can. You do whatever you want. I won't judge you. Let's see. So if we keep going and we want to really solve this problem, instead of just acting like an idiot here, then we would say in A, like, okay, zeros, this goes over here, we divide by a cosine, and we find the intermediate result is in A is sine theta over cosine theta in B. So that's like one equation. Can NA and NB be negative? No. Those are magnitudes. Those have to be positive. That is the relationship between the two vector magnitudes. All right, but we have two unknowns, but we also are going to have two equations. Why was the weight force not good? Oh, we did it. This thing warns me twice. Such a good question, my phone wanted to hear it again. Okay, so now we're going to do the y components. Okay? See what we get. So we also have 0 net force in y. All right? Let's see what that gives us. So now we're going to do the same thing. We're going to say n ay plus n by plus mgy equals 0. See, I meant to bring in the mg here, but you're right. I should have had it in here. I was also assuming things. So mgx is what we determined to be 0 up there. Okay, so let's see. Nay is what? Well, we have it in polar. We need it in Cartesian, and we know this is theta, and we know the definition. It's just Na sine theta. All right? So this is a component that can be negative. This is a magnitude. All right? What is the proper mathematical definition of the y component of this? It's NB sine of theta plus 90 again, because that's the angle all the way over. NB sine of theta plus 90. I should be saying pi over 2, I suppose. Okay. And now, what about mg? Okay. Here's another question. Do you put a negative on the mg? I don't know. Right? It's a little scary because I can say, don't put a negative on these. It'll tell you if there's a negative. But these are like vector components that could come out negative. mg isn't going to come out negative. Right? We know what m is. It's positive. We know g is defined as positive. How are we ever going to get this thing negative? We know it has to be negative. But you just do the rules. You say plus the magnitude, mg, times the sine of, like we just said a minute ago, we spoiled it over here, negative 90. Right? Sine of negative 90 minus 90. All those have to be equal to 0. And what is the sine of negative 90? Negative 1. Okay. Can you explain how you got the angles again? Let's see. I would need like where's their room? So I think of it this way. If the ball was here, this would be NB, and this would be this would be, what the hell did I call them? Which one's A? This is NA, and this is NB. And we tilted it, right? We tilted the whole thing this way. Then NA got tilted by theta, right? And NB got tilted by theta. So they both tilted this way by theta. Right? So, oh wait, did I switch up NB and NA? Let's see, what did I do? I switched them, sorry. Oh my God, never mind, for that clarifying moment. Okay, it's over, never mind. I screwed it up too much. No, I can't explain it clearly. Why is it negative 90, not 270? Because it could be either one, the same thing. Okay, so this is the origin of angles. We can go this way and call it negative. We can go this way and call it positive. It's less chalk if I make it negative 90, so that's why. Okay, so we just keep going. We don't want to spend our entire day on this. NA sine theta plus, what's the sine of theta plus 90? I don't have Google, I forgot, is cosine. Plus NB cosine theta minus mg equals 0. That's what you'd probably just write if you were left to your own devices, right? So I showed you why it all happens. Okay, we laid it out. And now we just do algebra. Now we say, okay, this is basically the answer here. So we say, let's just plug in NA here. So sine theta over cosine theta. Now this is just the algebra part, not very exciting. NB times the sine of theta. So all I did is I took that and stuck it right there. Plus NB times the cosine of theta minus mg equals 0. And now I'm going to pull a physics trick here. I'm going to multiply the whole thing by cosine theta. Is that allowed? Yeah, sure. Why not? Why not? Multiply the left by cosine theta. It cancels that 1 on the NB, and you got NB sine squared theta. And then plus NB cosine squared theta. cosine squared theta. And if you'll allow me, I'll put the mg on the other side and multiply it by cosine theta. And you get mg cosine theta. Right? And then you pull an nb. And you get sine squared theta plus cosine squared theta equals mg cosine theta. And what's sine squared plus cosine squared? 1. So you get nb equals mg cosine theta. All right, so that is the value of the normal force in terms of m and g and theta. Right? That's the nb normal force. And you want the na normal force. Oh, you just go there, you multiply by sine over cosine. The cosines cancel, and you get that na is mg sine theta. All right? So there's like, it took 3 boards to do something you would normally do super fast. But you got to do 3 boards if you want to think very carefully about vectors, and then vector components, and then calculating vector components. It takes a long time. That's why we usually just do it quick. So when we're doing it quick from now on for fun, we'll try to identify, is this a component or a magnitude or what? But knowing how to really do it can help you not get in trouble when things get complicated. Okay?